This is the momentum video 2. We're going to start this one by talking about conservation of momentum. So within a system, the total momentum of all the objects in the system will remain the same. So remember that a system is an object or a collection of objects. Objects are treated as having no internal structure. So a collection of particles in which the internal action changes little or not at all, or in which changes in these interactions are irrelevant to the question addressed, can be treated as an object. So that's just a quick little definition or a discussion on the systems here. So within the system, the total momentum will be the same. So if a quantity is conserved, like mass or energy, or now momentum, then no matter how complicated the situation, we can always set the value of the conserved quantity at one time equal to its value at a later time, kind of like a before and after. The new conserved quantity, momentum, is a vector, and that's where it becomes a little different than conservation of mass or conservation of energy. Remember that energy and mass are both scalars. Momentum is a vector, so direction also matters when we do conservation of momentum. So when momentum is conserved, both the magnitude and the direction of the momentum must be constant. So some more of this knowledge here then. For all systems under all circumstances, energy, charge, linear momentum, and angular momentum are conserved. Angular momentum is something we will talk about in the next grading period. So for an isolated or closed system, conserved quantities are constant. So a closed system, a system is a collection of objects. So if a system is closed or isolated, that means that there's no interaction with objects outside of that system. An open system is one that exchanges one of those conserved quantities with its surroundings. So if it's exchanging energy or charge or mass or momentum, then it would be an open system. An interaction then can be either a force exerted by objects outside the system or transfer of some quantity with objects outside of the system. So a system can interact with objects outside of the system. Think of asteroids hitting the Earth. What's kind of cool is that the boundary between a system and its environment is a decision made by the person considering the situation. So you can consider asteroids hitting the Earth as objects outside of the Earth system hitting it. Or you can take a look at as the entire solar system as one system, and then an asteroid hitting a planet is just an interaction inside of that larger system. You are free to decide the boundary of your system. In certain problems, it becomes easier if you make the boundary bigger or smaller. So consider two pucks that bump into each other after sliding along a frictionless table. There's a before the collision and an after a collision. And what we want to make sure is that all of the momentum, and since there's no friction here, it's just a two puck system. So this would be like the boundary of my system, and this would be the boundary of my system. So I'm not considering friction because it's frictionless. If there was friction, I would consider that an outside force outside of my system, taking momentum away from my system. But it's on a frictionless table, so this is my system, just that two puck system. Now, until the contact is made, there was no interaction between the two pucks. During the collision, the pucks exert forces on each other, so F1, 2 would be the contact force acting on mass 1, and force 2, 1 would be the force acting on mass 2. And the 1, 2, 2, 1, it doesn't matter if you get them mixed up as long as you're consistent throughout your problem. Now these forces, because they are internal forces inside a system, are interacting pairs, so that means that they will be equal in strength, opposite in direction. And again, I don't like to give things names, but it'd be described by Newton's third law. So when they collide, some of the momentum is transferred from one puck to the other. This changes the momentum, or the changes in momentum of the two will be equal and opposite. So for this system, I should have a total amount of momentum. not net force, net P this time. So the total amount of momentum for this system starting out will stay the same. So if, I don't know, there's like 200 kilogram meter per second worth of momentum in this system before the collision, there should be 200 kilogram meter per second worth of momentum after the collision. But remember, momentum is a vector. So the direction part has to be conserved as well. We'll get to that in a minute. All right, so if I take a look at this then, the changes in momentum of the two should be equal and opposite. So if I take a look at the change in the first puck's momentum, that will equal negative change in the second puck's momentum. So this is what our conservation of momentum would lead us up to. So what I can do just a quick little bit of math here. So change in momentum will be final momentum minus initial momentum. So I can do my final minus initial. I can distribute out that negative. And then I can rearrange things. And this gives me something important right here. And what this means is that all of the initial momentum of the system should equal all of the final momentum of the system. So, basically, these two things are the same thing. So the sum of the momentum after the collision equals the sum of the momentum before the collision. So the total momentum is conserved, a before and after. So this explains why guns have recoil. So taking a look at this first scenario, this before scenario, the sum of all momentum equals 0 because everything's at rest. The gun is at rest, the bullet is at rest. They both have mass, but they're both at rest. So the sum of all momentum is 0. In the after scenario, we see that the bullet is given some momentum. So the gun must get some momentum. So in other words, what I would say is that 0 equals the final momentum of the gun plus the final momentum of the bullet. Or I could see that the final momentum of the gun equals negative final momentum of the bullet. Now the negative sign is because they're going in opposite directions. Remember, direction matters. So I would have like a mass of the gun, velocity of the gun equals mass of the bullet, negative velocity of the bullet. And that negative sign just means direction. So if I assigned everything in this direction to be positive and everything in that direction to be negative, it would work out. And looking at this, notice that the higher the velocity that you give the bullet, the higher the recoil velocity of the gun would be. If you gave the bullet a greater mass, the gun would have a greater recoil velocity. I can also take a look at this using the other way, where I can say that the change in momentum for the gun equals negative change of momentum for the bullet. So I would see I have some final momentum for the gun minus some initial momentum of the gun equals negative final momentum of the bullet minus initial momentum of the bullet. Because they were both at rest initially, there is no initial momentum. And I arrive at the same thing, where the momentum of the gun equals negative momentum of the bullet. Okay, now let's consider direction. So here I have two pucks colliding again. Notice that A is slightly smaller than B, so when A strikes B, A is going to be deflected at an angle of alpha, and then B is going to be deflected at an angle of beta. So we have our before the collision and after the collision. So to analyze this, I would say that the change in momentum for object A equals negative change in momentum for object B. And going down through this, then I would have some final momentum for object A minus some initial momentum for object A would equal however, object B was initially at rest, so its initial momentum goes away. So I'm just left with that right there. Now these are vectors. So when I take a look at the momentum vector for object A, it's pretty standard. So before, what I have is I have this vector right here. I have this initial momentum of vector A. I'm going to say that's in the x direction, plus 0 momentum in the y direction. I think we'll move this. So that's what I had before. After, now I've got two things going on here. I have one vector going up like this. So I can break this up into a y component and an x component. Object B has a momentum that I can break up into a y component and an x component. So in the after scenario, what I have is for object A, it'd be like this PA, or momentum A times cosine of alpha plus, oh, that's in the x hat direction, so that'd be the vector describing the final momentum of object A. And then for object B, I have that. And then I could add those two together. And what I should find is that all of the final momentum should equal all of the initial momentum that I had. And once again, we'll take a look at some problems in class to get a better feel for this. We'll plug some numbers into this. we'll run through a scenario, and hopefully by the time you're done, everyone will be expert at playing pool, because really, if you think about it, this describes how to play pool. You know, figuring out these momentums and these vectors and everything else. Um, so that's going to conclude video 2 on momentum.